We've lost 1 billion years of our planet's history, and this mysterious gap, known as the Great Unconformity, continues to puzzle scientists. Glaciers may have erased a significant part of the geological record, paving the way for the Cambrian Explosion, the most crucial period in the evolution of life. Have you ever turned your house upside down in a desperate search for your car keys? We've all been there, losing our phones, wallets, or even our sanity. But believe it or not, the biggest mystery we face isn't a misplaced item. It's the fact that we've somehow lost 1 billion years of our planet's history. This isn't just like finding your keys in the bread bin. We're talking about a massive, mind-boggling gap in Earth's timeline. 1 billion years is nearly a quarter of our planet's entire existence. Yet there's this enormous blank spot in the geological record that scientists refer to as the Great Unconformity. Intrigued? Let's dive deeper. Imagine if you started digging right now in your backyard. The deeper you dig, the older the layers of rock you would find. You might start with relics from recent decades, like a cassette tape from the 90s or a disco ball from the 70s, but keep digging, and you'd hit upon ancient Roman coins and even older artifacts. So why do both man-made and natural objects end up deeper in the ground over time? The answer lies in a process called sedimentation, where fine particles like sand and dust gradually accumulate on the Earth's surface. This happens excruciatingly slowly, and eventually these particles undergo cementation, binding together to form sedimentary rock over millions of years. This rock formation process is like making a geological trifle, with layer upon layer of rock stacking up over eons. Unfortunately, no custard included. As these layers form, animals die, and while their softer tissues decompose or get eaten, their harder parts, like bones and shells, become buried under sediment. Over time, these remains get encased in rock, and water infiltrates, dissolving the biological material. Minerals then fill these voids, creating fossils, essentially rock replicas of the creatures that once lived. These fossils are like time capsules, preserved in the sedimentary layers from the eras in which these animals existed. Our entire understanding of Earth's history and the evolution of life comes from studying these rock layers and the fossils they contain. It's a fascinating journey through time, unearthing the secrets of our planet, one layer at a time. Often the various layers of rock, known as strata, are distinct, and each layer reveals something unique about the time period it was formed in. The fascinating field that studies these layers is called stratigraphy. One of its fundamental principles is the law of superposition, which simply states that in an undisturbed sequence of layers, the deeper the layer, the older it is. It's not exactly rocket science, but it does help create a fairly accurate timeline when examining geological formations. However, Earth's history isn't always straightforward. While sedimentary layers are forming in one place, conditions elsewhere can change, halting sedimentation. Erosion from wind or water can carry particles away, effectively erasing part of the geological record. Sedimentation might resume later, but these interruptions, known as hiatuses, leave gaps that can span millions of years. Imagine hitting pause, rewind, and then record during a long conversation. The final recording will have missing parts, disrupting the flow and meaning of the conversation. These hiatuses create noticeable differences in the angles, colors, and textures of the rock layers. Geologists refer to these features as unconformities. The concept was first sketched by Niels Steensen, the father of stratigraphy, in 1669. But it was Scottish farmer James Hutton who discovered the first significant unconformity at Sycamore Point in Scotland in 1787. He noticed a striking difference between the lower and upper rock formations and named it Hutton's Unconformity. The lower grayish layer consisted of deep-sea deposits from around 425 million years ago, while the reddish upper layer was formed by rivers and streams about 345 million years ago, an 80 million year gap. Hutton's discovery was pivotal in developing theories about tectonic plate movements and the forces shaping Earth's surface. Some geologists even consider Sycamore Point a geological shrine due to its significance. But perhaps the most astonishing unconformity was found in 1869 by John Wesley Powell while exploring the Grand Canyon. He observed vertical rock formations adjacent to horizontal ones, providing a clear and dramatic example of how geological processes can create such profound gaps in the rock record. These unconformities remind us that Earth's history is complex, full of interruptions and gaps that challenge our understanding, but also reveal the dynamic processes that have shaped our planet over billions of years. Channeling the creativity of his geologist predecessors, he dubbed it Powell's Unconformity. However, it's more commonly known today as Powell's Great Unconformity, and there are two compelling reasons for the great title. Firstly, This unconformity stretches across an entire continent, spanning Laurentia, the ancient core of North America. Secondly, unlike many other unconformities that represent relatively small gaps in geological time, perhaps tens of millions of years, the smallest gap in the Great Unconformity is a staggering 250 million years. The largest, over 1.2 billion years. Yes, you read that right. This massive missing chunk of Earth's history, nestled between two seemingly ordinary rock formations, represents up to 1.2 billion years of lost time, and we have no clue where it went. But the story doesn't end there. Since Powell's remarkable discovery, similar formations have been found worldwide, all sharing this mysterious time gap. Collectively, these are referred to as the Great Unconformity, a planetary puzzle spanning over a billion years of missing geological records. For instance, in the Grand Canyon, the 525 million-year-old Cambrian-era tapeite sandstone lies directly atop the 1.7 billion-year-old Precambrian Vishnu basement rocks, revealing a gap of 1.2 billion years. Travel to the Ozark Plateau in Missouri, and you'll find a similar scenario where 500 million-year-old sandstone rests on 1.4 billion-year-old granite, marking a 900 million-year hiatus. These gaps are incredibly perplexing. What on earth happened here? One prevailing theory to explain the Great Unconformity is the snowball Earth hypothesis. During the Cryogenian period, around 650 million years ago, the Earth's surface is believed to have been covered by glaciers and ice sheets. These glaciers could have caused extensive erosion as they moved across the landscape, potentially removing 2 to 3 miles of the Earth's surface. Essentially, the planet underwent a massive exfoliation. Remember when I mentioned that the younger rocks sitting atop the Great Unconformity date back to the Cambrian period? What's particularly fascinating is that the Cambrian period witnessed the most significant explosion of life in our planet's history, known as the Cambrian Explosion. This era saw a remarkable diversification of life forms, marking a crucial turning point in the history of life on Earth. So not only does the Great Unconformity represent a colossal missing piece of geological history, but it also sits right before one of the most critical periods in the evolution of life. During a brief span of about 11 million years, between approximately 541 and 530 million years ago, the early ancestors of nearly all modern life forms emerged. This period saw the first appearance of fish, among other life forms. While there was life before this era, this short window was a time of extraordinary evolutionary activity, akin to nature hitting an evolutionary turbo boost. How does this connect to the snowball Earth theory? Well, as these massive ice flows melted into the ocean, they released vast amounts of nutrient-rich minerals into the water. The theory suggests that these nutrients fueled the explosive diversification of life during the Cambrian period. Essentially, glaciers eroded over a billion years of sedimentary rock from Earth's surface and deposited it into the oceans, where the minerals within acted as a catalyst for the rapid evolution of life. In a way, it seems we did misplace a billion years of history, but instead of being lost down the back of a metaphorical sofa, it ended up at the bottom of the ocean. However, it's important to note that the snowball Earth theory proposed by Dr. Paul Hoffman in 1998 is still just that, a theory. While it offers a compelling explanation, 2 decades may not be enough time to fully unravel a billion years of missing geological history. Have you ever pondered how much of Earth's history remains hidden beneath our feet? The mystery of the Great Unconformity, a colossal gap in the geological record spanning up to 1.2 billion years, continues to baffle scientists. This missing chunk is not just a minor oversight. It represents nearly a quarter of our planet's history, lost to time and geological processes. As we dig into this enigma, it's fascinating to note how rock layers, or strata, tell the story of Earth's past. These layers form through sedimentation, where fine particles like sand and dust accumulate over eons, gradually cementing into sedimentary rock. Each layer holds clues about the environment and life forms that existed when it was formed. However, the Great Unconformity disrupts this narrative with a substantial gap that geologists are still trying to explain. James Hutton's discovery of unconformities, like the one at Siccar Point in Scotland, was a groundbreaking moment in geology. He observed a striking difference between 2 rock layers, revealing an 80 million year hiatus. This finding helped develop our understanding of tectonic plate movements and the dynamic forces shaping Earth's surface. Moving forward to John Wesley Powell's exploration of the Grand Canyon, we find the most dramatic example of the Great Unconformity. Here, 525 million year old Cambrian-era tapeite sandstone lies directly atop 0.7 billion year old Precambrian Vishnu basement rocks, showcasing a staggering 1.2 billion year gap. This discovery underscored the immense scale of the missing geological record. One compelling theory to explain this gap is the snowball Earth hypothesis. During the Cryogenian period, around 650 million years ago, glaciers covered much of the planet, causing extensive erosion. These glaciers likely removed vast amounts of sedimentary rock, depositing nutrient-rich minerals into the oceans. This influx of nutrients could have triggered the Cambrian Explosion, a period of rapid diversification of life forms. Imagine the profound impact of these events on the course of evolution. The Cambrian Explosion saw the emergence of nearly all modern animal lineages, fundamentally transforming life on Earth. The connection between glacial activity and this evolutionary burst highlights the interplay between geological and biological processes. As we continue to explore and develop new technologies, we may one day uncover more details about the Great Unconformity and the missing billion years of Earth's history. Until then, this mystery remains a captivating puzzle for geologists and curious minds alike. Thanks for joining me on this journey through deep time. Perhaps future advancements in technology and techniques will provide new insights, allowing us to fill in more of the gaps in Earth's long and complex history. Until then, the Great Unconformity remains one of the planet's most intriguing mysteries.